Okay, so we'll continue with VCO Design, okay, in today's class. Okay, so before that, I think some of you had questions about the noise injected into the tank, about why it causes amplitude shifts and phase shifts at different points. So I couldn't think of a better way to explain it qualitatively, so I just calculated out the, what happens in the tank when you inject some noise, inject a current pulse. So we have the ideal LC tank, and we're going to inject some noise In of t. What is In of t? We're going to assume it's some of the form. It's injected at a time t, and the value of the pulse is delta q. Okay. So what this means is the charge transferred is delta q into the LC tank. Okay. So what happens to this current pulse? So it tries to split between the inductor and the capacitor, but of course the inductor current cannot change suddenly, okay, because it would produce an infinite voltage. So all the current pulse will flow through the capacitor, okay. And for the capacitor, you will have a delta V, which is a voltage step, okay, at t equals tau. So what we'll do is we'll assume that so let's say this is VO of t. Let's assume initially VO of t is V naught cos omega naught t. We'll assume it has some sinusoid on top of it, right? And we are injecting a pulse into it at a time tau. Okay. Now the system is linear, so we can actually use superposition to calculate out the final point. So what happens? So you have a charge here. So what happens? The charge goes back and forth between the inductor and the capacitor at a frequency. So you'll have, use superposition. So you'll have is delta V, right? At tau, you have a peak charge on the capacitor. So it will go with a sinusoid, which is delta V cos omega naught t minus tau. Okay. So this will just be delta V cos omega naught t minus tau. Okay. So now of course this will have two components. So you can create a something times right, you can split it as something times cos omega naught t, something times sin omega naught t. So obviously you're going to have some amplitude shift and phase shift. Okay. So the final expression is, let me see if so if VO effective is, if it's this, V happens to be 1 minute. Plus delta V this is the amplitude, and the phase is tan inverse okay. So that's the amplitude and the phase. Okay. So now you can show, you can put in tau equals 0 at t, right, and tau equals pi by 2. So if you put in those two values, you will find that if you put in tau equals 0, okay, which means it's hitting at the peak of the sinusoid, what you will find is phi will turn out to be 0, okay, and V will turn out to be V naught plus delta V. So all the energy goes into raising the amplitude. And then of course now you can take this phi and maximize it for what tau you get maximum phase shift, and that will of course happen when tau is pi by 4, sorry, pi by 2, okay. So that is the quantitative way. I couldn't think of a really qualitative way of explaining it. This is a lot straightforward, lot more straightforward. Okay, so coming back to VCO design, so let's just do a quick table wise comparison of the Colpitts versus the cross coupled oscillator, because you guys will need to know which architecture to choose and why you are choosing it, okay. So it's called the cross coupled or negative GM oscillator, the Colpitts, okay. So let's start off with the frequency of oscillation. Sorry. So one of them is 1 over 2 pi root LC, the other is 1 over 2 pi root LC equivalent. So nothing much to choose between the two, right? You can choose L and C values properly, so that's not a big deal, okay. What is V naught? So if you take the NMOS oscillator, it's 2 by pi IT times RP, right? What is it for this guy? Sorry, one more. You remember this expression, 2 IT RP times 1 over 1 by N, okay. It so turns out, if you want best phase noise performance, it happens approximately around 1 by N equals 0.2, okay. The tap ratio is 0.2, okay. So this happens to be 1.6 IT RP, this happens to be okay 0.64 IT RP. So this the Colpitts is better as far as amplitude goes for a given current and a given RP. What is the startup condition? Startup condition is, for the cross coupled, GMRP is greater than 2 was the startup condition, where you are assuming that you have a single L which is split as L by 2 on both sides, okay. You can calculate out the startup for the Colpitts oscillator also. We have not done it in class, but you can do it, okay, because you know the negative resistance at the frequency of oscillation. You can calculate it out. It happens to be greater than 1. GMRP greater than 6.25, okay. So definitely the cross coupled is way better as far as startup condition goes, which means you need a lot more gain for startup in the Colpitts, okay. Okay, let's look at the tuning range. So If you have an NMOS only oscillator, it's pretty good. You have a varactor, you have a fixed capacitance, which is mainly just the capacitance of the tank. The capacitance of the transistors. Okay, so the inductor will have some parasitic capacitance, but that will usually be much smaller. You'll usually be dominated by the CG of the transistors. So the PMOS transistors, obviously they are going to be thrice as large as the NMOS transistors. Tuning range is obviously impacted, it's okay. Complementary is also okay, again you have PMOS plus NMOS. In the case of this guy, the tuning range is poor. Why? So you need some fixed cap for the impedance transformer. Okay, for the tap ratio you need fixed cap. Okay, so that creates a problem because you need to add extra fixed cap apart from the transistor capacitance. Okay, so definitely as far as tuning range goes, you choose the cross coupled. Phase noise wise, the cross coupled is decent, it's good, but it turns out this has better phase noise. Now that is a little bit subjective because you really need to trade off, you are effectively trading off tuning range for phase noise, but the phase noise can be slightly better for the Colpitts. Okay, because remember that the noise is injected at the peaks of the sinusoids, of the cosinusoids. Okay, of course the cross coupled, the circuit is automatically differential. This is single ended, but a differential version is possible. Okay, definitely you can put together two things, create virtual grounds between the differential pairs, and you can do it. That's very straightforward. Okay, so there is actually a pretty good paper available. If anybody wants, I'm anyway putting it up on the class website. If you want, you can take a look at it. Okay, so this basically tells you which one is which one to choose depending on what your spec is. If phase noise, if you don't care too much about tuning range, phase noise is the most important thing, you'd probably want to go with the Colpitts. If your tuning range is fairly important, then you'd probably want to go with the cross coupled anyways. Okay, even though phase noise is a little bit worse, and that's why you'll see that most people in the industry, they end up using the cross coupled version, because the way things are moving towards like a multi-band or a multi-mode transceivers, right? So what happens is, if you need the VCO to operate from, let's say you need the same VCO, the same PLL to operate, let's say from 800 megahertz all the way to 2.5 gigahertz, you don't have a choice. Okay, otherwise you're going to end up using two large inductors, two large capacitors and so on, right? So most people end up choosing the cross coupled version. However, if you go to the discrete circuits, they end up using the Colpitts, because there you are more interested in the single ended version. There are a lot of ways, if you start going discrete, you can find ways to make it, split the power into 0 and 180 and so on, right? There are power splitters, microwave power splitters available. Okay, so now what we'll do is, we'll go circuit by circuit, portion by portion of the VCO circuit, and see what your options are for each one of them. So first, let's start off with the VCO biasing. That's the most basic thing. Okay, so the simplest way to do it is use a current mirror. Okay, so let's try to draw the equivalent circuit of the VCO as seen by the current mirror. What does it look like? So you have M1 and M2 are switching back and forth at the rate of omega naught. So what does that look like to you? What does this look like to you? This actually looks like a mixer, right? This is the equivalent circuit we made for a mixer. Okay, so what that means is any signal or any noise, which is more important, is going to get upconverted around omega naught. Okay, remember that the noise of this transistor looks like this. Okay, so flicker noise ends up getting upconverted to the VCO frequency. So part of the flicker noise in this region comes from the transistor, from the bias transistor. Okay, now the next question is, we are analyzing it like a mixer. So the next question is, so let's say this is which current? Tail current is constant, but along with it you also have a flicker noise, right? So that flicker noise ends up also gets multiplied with this omega naught switch between the two paths. Okay, now what happens to your, so you have some noise around 2 omega naught. Remember that if you have a mixer, you have the signal, you also have the image. Okay, so it turns out you have noise from 2 omega naught, which is also down converted. Okay, down to omega naught. Okay, so now the only thing you have to be careful about is analyzing it to see if it is actually going into amplitude noise or phase noise. So that analysis, I mean, it's people have done it. I can show you the information, but it's just one thing to remember. Even if you have part of it goes into amplitude noise, because you have the varactors which are tuning. If you have any amplitude noise at this point, okay, the varactor is going to convert it to phase noise, because the varactor capacitance varies as a function of the DC voltage. Okay, but it will respond to any low frequency things, variations. So if you have any low frequency variations, it will end up causing PM noise. Okay, we are going to look at that a little bit later in class. Okay, so what can you do to improve this? Of course, I mean, the first thing to do is increase W and L, right? To make sure that you have very low flicker noise from the bias. And of course, keep your VD-SAT low. That is of course obvious. So while meeting the VD-SAT spec, increase W and L. Basically increase the area. So what you will see is, let's say, quite often you will see bias transistors all the way up to 1 millimeter over maybe 1 or 2 microns. That's very common. Okay, because you need to meet both VD-SAT and, so several hundreds of microns are definitely normal. Okay, so now the next thing, so we talked about 1 hour of noise from MCS2. So let's say this is IT. Okay, how about MCS1? So let's say this is a 1:1 mirror ratio. Okay, how about MCS1? You are definitely going to see, because MCS1, the flicker noise is going to appear as a voltage, that's also going to get mirrored over. Okay, so you are going to see noise from MCS1 also. Okay, Let's look at a second case. If you go back to the figure, with a 1:1 mirror ratio, you're actually wasting, same current as IT in the mirror branch. Okay, that's obviously not acceptable, because if you have 2 milliamps in the VCO core, you can't double the power by saying you have that much in the bias path. So you're going to create some. Okay, you're going to create some 1:n mirror. What is that? What that means is, this is going to have 1 over n W over L, which obviously means the flicker noise is going to get worse. So the device is much smaller, right? So it's quite common to see, the mirror ratio of maybe in the tens, okay, maybe all the way up to 100. So if you're burning maybe like 2-3 milliamps here, you don't want, so let's say 3 or 4 milliamps, you don't want to burn more than 30-40 microamps, okay, in the side path. 1 or 2% increase in power is what you can tolerate. But then what that means is, the flicker noise of this guy comes into play. Okay, what can you do? So what you can do is, okay, before we go back to this. So one way to do this is to remove the bias. So you may be tempted to just remove the bias and have something like this. And this has been done. Okay. So you try to have a tapped resistor ladder. So depending on how much bias current you want, you can switch on more or less of the resistance. Okay. So of course, you don't have any 1 over F noise. Obviously, you only have resistors now. Now your first problem is, you have bias current variation over PVT. Your bias current is no longer constant. It depends on the VGS and the resistor values. Resistor values will change with temperature and process. And your same thing with your transistors. PVT variations will change the VGS. Remember that the bias point of the output, let's say in the case of an NMOS transistor, is VDD, right? So you have VDD minus VGS coming across the resistor. That's what you're using to set up the current. Okay. The other problem, let us say you could have, so let's say the ground is shared between this circuit and some other circuit. You could have some kind of disturbance on the ground, and that will get translated through the resistors through the current. Whereas if you had a current source, naturally the output impedance is high. Okay, so you would have some rejection, whereas in this case you would have no rejection at all. Okay, people have done this, but it's not the preferred solution. So the typical solution would look like this. Okay, would look something like this. So this will have a mirror ratio 1:n. Okay, so let's say n is 100 in this case. You could have so you have this, you don't have any wastage of current. Now you want to take care of the flicker noise of MCS1. So you are going to put an RC filter to take care of the flicker noise of MCS1. Okay, What kind of RC values do you think you need to get rid of flicker noise? So let's say you want to get flicker noise, you want to get rid of flicker noise down to, you obviously can't get all flicker noise, right? But you have a certain corner up to which you can take care of, right? And that's typically decided by, obviously your in-band of the VCO is going to matter less because your PLL is going to reject the close-in noise of the VCO, okay? So once you put it in the loop, your PLL is going to reject the close-in noise of the VCO, but you still have a certain spec because it will be additive, there will be some rejection from the PLL. And then, so depending on at what offset, at the closest offset you have a noise spec, you try to push in the 1 over of noise based on that, okay? Typically, the RC corner, the bandwidth would be few hundreds of hertz, okay? Maybe, I mean, there might be some applications where you might want to have, you might be able to go all the way up to a few kilohertz, but this will be the typical number. Yeah, we are going to look at it. Yeah, of course. So we'll take a look at it. Unfortunately, you don't have a choice, okay, because you are more worried about noise than area at this point, and it's still better than going with a different architecture which may require 2 inductors, okay. So quite often, if you actually look at the lot of journal papers or conference papers show you the layout. If you look at the layout, obviously the number one thing you can see is the inductor of the VCO, okay, and surrounding it you will see a lot of these big yellow squares which may look like they don't mean anything. They are typically the capacitors, okay, they are typically the bias filter capacitors. That's very common. Now, if you're doing research, you may not worry about this because this is very standard implementation in the industry. So if you're building a VCO, trying to build a prototype, you wouldn't worry about this. You would just make the transistor the same size as this one and just go ahead and put in the same current, because that is the current you're controlling is from, you're controlling it and you don't care about the current spent outside the VCO. But if you're really building it, you would have to care about it as part of a bigger system, okay. So, I thought the basic thing is we wanted to keep the area down, right? Why would you want to use an LC there, right? And of course, imagine you actually want to get a low pass filter, right? An LC would give you a, right? Well, an LC would give you something, but to get the same low pass characteristic, you would probably need to have a much larger L, right? So in this case, of course, the L is series and C is shunt, so you will get a low pass response. But to get the same, filter bandwidth, you need a much larger L. Okay. Yes. What kind of noise? Exactly. So if you look at the noise, remember that if you have a filter, the total noise of the output is KT over C. Okay. So the first thing you would want to do is keep the C large, and that's why we have chosen 2 megohms and 400 puff instead of choosing 10 2 megohms in series and a 40 puff capacitor. Okay. So keep KT over C in mind. Okay. So you need to keep the cap large. Okay. Okay. Now the next thing you will see is, if you want to get a 2 megohm resistor, okay, it starts becoming pretty big. A 2 megohm resistor will probably be as big as probably a 10 puff capacitor or something like that. Okay, depends on the process, but it will be pretty large. So you don't want to implement it using resistors, real resistors, and there is actually an easier way. Okay. So something you could use something like this, where something like this. You could have where the width is 0.5 but the length is 10 microns. Okay, so you're effectively creating a very large resistor using transistors. This will be much more area efficient. Okay, and of course you want to use PMOSs, but you have to be careful. You'd be able to use PMOSs if the voltage, input voltage is, at a certain point, right? Remember that PMOS can't pass voltages below VT, but that is not a problem here actually. So, right, PMOS can't pass voltages below its own threshold voltage, but the NMOS threshold voltage may be different, so you have to be careful. Okay, so the next problem you have from this is, so let us say you are now going to start up the whole system. Okay, so let us say you use either the resistor or this NMOS. Now you obviously have a very, very large RC. Okay, so the input, the VGS for the MCS1 gets established immediately. Okay, the time taken for turns out to be approximately 800 microseconds before the output current settles on the other side. Okay, so the minute you do this, you would need to have some kind of startup circuitry which helps the current get established immediately. So you'd have to have something like this. So the gate of this transistor would be a pulse. So this would be, let's say, t equal to 0, and you could choose a certain point, let's say t equal to 15 microseconds or something like that. So you can give a specific time. I want the VCO to start up within 15 microseconds. You'll have to size the transistor accordingly, right? Now you have a new RC time constant, resistance of the transistor and the capacitor. Okay. Of course, the other option is you can also have, just remember that you can also bias it using PMOSs, and quite often you will see that PMOS transistors have lower 1 over F noise. Okay, that's very, very common. But of course, now for the same VD set, your PMOS transistors will have to be much larger. That is a natural trade-off. Okay, so that's as far as bias goes. How about your, okay, so let's come back to your now you need to choose your IT properly. Okay, IT as well as the LC. So you don't have any, so it seems like you can choose any inductor or any capacitor, right? Or rather any inductor for the required omega naught. Okay, so we want to find out a good way to determine what that inductor should be and what the bias current should be. So let's plot V out, which is the oscillation amplitude, versus IT. Okay, it will look something like this. In this region, it's 2 over pi IT RP, but eventually you are going to be limited by the either the supply rail or the VD sat of the lower transistor. One of those two things you will be limited by. Okay. So you have two regions of operation. Okay, so this area is called the current limited region of operation. This area is the voltage limited. Okay. So what happens if you keep increasing the, so if you keep increasing the current, the voltage doesn't change. So any extra energy you put into the system will typically go into, so what will happen is instead of a sinusoid, you'll now start having, the energy will start going to the higher harmonics. Some of the energy will start going into noise. So effectively your SNR will only get worse in this region. So ideally you want to operate here, okay, at the boundary between the current limited and voltage limited regimes, because you want maximum amplitude but you don't want to give too much amplitude. I mean, you don't want to give too much current for that amplitude. This is your optimum operating point. Okay. So now you can also choose, you can choose your complementary, because you know that it's actually going to have a higher slope. Okay, but just remember, okay, your complementary looks something like this. It's going to look something like this, but remember that in this voltage in an NMOS only transistor, okay, so the bias point is VDD, so the maximum it can swing is all the way down to 0 and all the way up to 2 VDD. Okay, so swing is going to be VDD. Okay, maximum amplitude. Whereas here, maximum amplitude is going to be 2 VDD, maximum swing. Whereas here, because you have VDD swing on either side, so you're going to have 2 VDD differential. Whereas on this guy, you're actually limited by the VDSAT of both the NMOS and the PMOS. You can never swing above VDD. Okay, so that is something you have to keep in mind. So the maximum swing possible is lower. Okay, so there may be cases where your NMOS can actually perform better than your complementary, because remember we talked about the complementary has more symmetric waveform, so 1 over of noise is better, but you could still have a case where 1 over of noise, the basic in the NMOS only transistor, the basic 1 over of noise is higher, but since the swing is larger, your phase noise could still be smaller. Okay, so you have to be careful. Okay, so you can choose either one of them based on this. We'll come back to this point. Okay, we'll come back to how we choose this optimum operating point, because obviously now you need to operate here, you need to choose a certain IT and a certain RP. Okay, so typically you would do it by choosing a certain current spec. Okay, that's your power dissipation, and then you would choose RP. How would you choose RP? RP is nothing but, so you're designing an inductor for a certain Q. Okay, so you want to get maximum Q. So let us say the maximum Q achievable in a certain process, maybe in our process it's like 11 or 12, right now. So what that means is, if you choose a Q of 11 or 12, choose the inductor such that you get the maximum RP, which means maximum inductance. Okay, of course you still have to be careful, because if you try to increase the inductance too large, then your capacitive parasitic of the inductor start come into play, your self-resonant frequency may go down, you have to be careful. Okay, let's go back to our NMOS only transistor. Okay, so other techniques which you can use is use a transformer. Let's say the coupling factor is K. Okay, differential current is going to flow through the circuit, let's say in this direction. So what's going to happen is the differential current is flowing into the dot point here, into the dot point here. Okay, so it's going to produce a positive mutual effect, mutual inductance. Okay. So your effective L is 1 plus K times, effective inductance is 1 plus K times L. Is that clear? So which means, so let us say it had a certain series resistance R, each inductor. So instead of omega L over Rs, you will have omega naught L effective over Rs. Okay, so you have effectively almost doubled. So your K coupling factor can be as large as 0.8, 0.9. So you are effectively doubling your Q. Okay. Of course, the other advantage of doing this now is, if you look at your common mode signal, it actually gives you it actually has a very, very low Q, because now you have 1 minus K times L is the common mode, because now the common mode current is entering the dot point here, leaving the dot point here. So the mutual effect is negative. Okay. So let's call this . Okay. So now tuning. We talked about the varactor tuning, right? Before that, you need to choose a certain KVCO. Okay. Now, if you choose all the variable capacitance as just the varactor alone, if you have just say one huge, let's say your tank capacitance was 2 picofarad. If you choose a 2 picofarad varactor, what you will get is KVCO will be hundreds of megahertz per volt probably, if I had to take a guess. Okay, but one problem from this you will see is, if you have such a large KVCO, such a large capacitor, what you will see is, if you have, so whatever amplitude noise you had at the output will get converted to a very large phase noise. Okay, and you won't realize this just by looking at the noise contributors, because what the simulator gives you is, if you actually run the phase noise simulation, it will tell you the noise contribution from this transistor or this resistor is so much. Okay, however, it won't give you the process through which that phase noise has come about. So if there is, let's say there is some current source noise, it has gone to the output as AM and then got converted through the varactor to PM, you will never see it. You will just see current coming from the noise, from the current source. You will be trying to change the sizes or the currents. You may not see a major impact. Okay, so you have to be very careful with KVCO. So normally, at least for wireless applications, you would have to choose a KVCO of a few tens of megahertz per volt. You don't want anything much higher than that. Okay, obviously the other reason why you don't want anything is, so if you look at the, so this is the model. If you have any noise or some harmonic leaking into a low frequency signal leaking into the VCO input, the larger the KVCO you have, the larger the gain to the output. So you want to keep that also small. You could have things coupling to the loop filter node after the loop filter. Obviously anything coupling in here will get attenuated by the loop filter. Okay, but anything after that will be a problem. Okay, so what happens is, if you choose one large varactor, so let's say the overall capacitance is 2 picofarad. Okay, so if you choose one large varactor, what will happen is, your KVCO will be very large, of course, right? If you choose one large varactor. Okay. So what you'll get is, you'll get a curve like this, and so let's say this is F0 versus V. Okay. Let's say you wanted to tune, right? So let's say from 1.5 gig to 2.5 gig. You'll get one large varactor. The varactor, VC change itself is probably going to be maybe 1 to 1.2 volts, not more than that. With a 1.2 volt supply, you can't expect, right, much more. You probably have much lesser. Okay. If you take our 0.13 process, the actual range over which this changes will probably be 0.7 to 0.8 volts, not much more than that. Okay. So what your actual KVCO will probably be at least a gigahertz per volt in this case, right? Now what happens is, if you have such a large KVCO, okay, this is your control voltage. In this case, the output is biased at VDD. Okay, the varactor is going to change any DC voltage across this. Okay, if you have a very large thermal noise in and around DC at the outputs, these two varactors are going to convert it to phase noise, because what the varactor does is, the capacitance varies as a function of this voltage. Capacitance varies, the frequency will vary. What does frequency variation with noise mean? It just means the noise sidebands around your VCO center frequency. Okay, so if you have a very large KVCO, so the gain from this point for noise, for AM noise from this point to the phase noise sideband is going to be very high. Okay. So let's say KVCO is 50 megahertz per volt. Okay. No, simulator will capture it perfectly. Okay, so you will see a noise hit. The thing is, what you want to see is how the noise is hitting you. So what I meant is, what the simulator will do is, simulator will show you a very bad noise at the output. Okay, so now the way okay, so how do you go about optimizing noise? So the way you do it is, in the simulator is, you run the phase noise simulation. Then let's say you are looking to reduce phase noise at a particular spot, let's say at 1 megahertz offset from your carrier. What you would do is, you would go ahead and the simulator is able to give you what all devices are giving noise, are contributing noise at that frequency. Okay, so it will give you the noise contributors. Okay, what it doesn't tell you is how the noise gets there. Okay, so whether the noise is directly going to phase noise, as we looked at the theory, or whether it's going to phase noise AM noise and then getting converted through the varactor to PM noise, it won't tell you. Okay, so you may be trying to optimize, the basic. So what I mean is, there are ways to optimize noise at the device level. You can, you might see 1 hour of noise, let's say. Okay, you might try to increase the device size and so on. But there is actually a much better way to do it without increasing the device size, which is reduce your varactor KVCO. Okay, that's the idea. So now what you do is, so you want to make your KVCO very low, let's say a few tens of megahertz per volt. So what you are going to do is, you obviously need a fixed capacitance. Okay, otherwise you can't do it. You need to have the varactor capacitance should be very small compared to your fixed capacitance. That's the only way you can get a very low KVCO. But you also want the tuning range. Okay, so what you are going to do is, you are going to use discrete tuning. Okay, so what that means is, so these varactors are going to be small. So you're going to use some kind of discrete tuning. So each one of these, you'll have a bank of capacitors with a series switch. okay, depending on the frequency. So you're going to get some amount of coarse tuning from the capacitor bank, okay. And what you're going to do is, if you want to go to a particular, operate at a particular frequency, you're going to turn on a certain set of fixed capacitors. Around that, you're going to tune over a very small range. That is what you want anyways. In most cases, that's what you want to do. You want to reach, you want the PLL to lock to a particular point and then control variations around that. So the switching of these capacitors would come through a different loop, okay, inside the PLL. Remember that the VC comes from your loop filter of the PLL. What will happen is, that is continuous tuning. However, as far as discrete tuning goes, you just want to do it once when the PLL is locking. After that, you don't need to do it, okay. So what you will do is, you will have a coarse tuning loop, okay. Now it's a loop in the sense, you're going to use a counter to measure the VCO output frequency, okay. You're probably going to have some kind of algorithm, maybe you might use maybe a SAR or something like that, okay. And you're going to turn on capacitors till you reach a certain frequency, okay. But you don't care, right? What do you need the tuning range for? So you need the tuning for a bunch of things, but the number one thing you need the tuning for is the PLL is you want it to remain locked at a particular VCO, you want it to remain locked at a particular frequency. However, you know that the VCO frequency varies with PVT. Okay, you want to compensate for those things and get a very stable frequency of oscillation at the output, and that's why you need this analog control voltage. So all you have to do is, you make sure that your KVCO is large enough to cover for those variations and you are good to go, okay. Okay, so let's stop here and then we'll continue next. Okay, actually before we stop, the one thing you need to know is, if you now look at frequency versus voltage, control voltage, okay, you're going to get a bunch of curves, because for each discrete capacitance you're going to get a bunch of curves, right? And that's what you want anyways. You just need to make sure there is, to make sure you have a continuous tuning, you need to make sure you have overlap between multiple curves, overlap in the linear region, obviously, okay. You need to have overlap in the x-axis, in the f-axis, frequency axis, so that you have a full coverage of frequency, okay. Okay, so let's stop here. We will continue next class. I think I still have a little bit more on the VCO. So actually, yeah, I still have a little bit, maybe 10 to 15 minutes. So we'll cover it next class. Okay.